record and action. So I had a few emails over the weekend. Nice to hear from you. The assignment that was due last night, was it that one or is it the next one that's acting weird? Either way, you have to submit each question. And like I was saying, I don't know what I need to change to make it just be one submit button. So I'll have to play around with that. But if you're ever unsure if it's transferred your grades over, they will be sent back to Moodle. It does take some time, sometimes, internet, right? But if you go into your grades on Moodle and they match what you're expecting to see, then it saved your work, okay? And in Mom, I can always hop in and pretend to be you, and I can see all the things that you've written. So even if they're not submitted, I can see that. I know, creepy, right? I can, if I have to, I can submit things for you, that kind of thing. So yeah, there's kind of a learning curve with using it, but I think we're getting there, and myself included. But yeah, so you can just go to, I don't know if it looks like this on your end, I assume it does, but you can just go check out your grades, and if you have the grade that you think you should have from doing the Mom test or the Mom assignment, then it's all good, okay? If not, get in touch with me. All right. Let's see, was there anything else I wanted to say there? No, I don't think so. All right. Oh, I'll close this door. No one uses that door. It's hidden. All right. So in terms of a little bit of review, not too much because I want to keep chugging away, and I know a lot of you have already started the 1.1 assignment, so that's awesome. It's not due until Sunday, next Sunday, or
Sorry, what was due last night?
just that intro to Mom quiz.
Oh.
I know, I'm not that mean. I give you a week at least from the time that we finish the material, unless there's a test and I want you to have the assignment done before the test. That's the only time where I really kind of crack the whip and make you work for it a little bit on a quicker schedule. But generally, I'll give you no less than a week to work on assignments. But now it's done. It's done. All right, so we did a lot of things, but what I want to come back to from last day was we introduced what we'll call the toolkit functions. And now, where are they? So we had a look at this, and in the interest of not copying and pasting that into the notes again, we'll just have a look here. So this is what we introduced last day, and I said, okay, well, just like you can recognize a triangle and a square and a rectangle, a rhombus, I don't know, just all those shapes, right? We need to be able to look at a graph, for example, and match it to one of these toolkit functions. And that's why it's part of the toolkit, is because most things that we're going to see are going to be based off of these functions here. So although we didn't see the graphs last day, I'm going to kind of bake it in as part of our review. Okay, so what do these things look like? Let's see if I can. Well, first of all, that was just for me. Let's start with the ABCs, so to speak. Yeah. The most basic toolkit function that we could talk about is a constant function. Usually we have just f of x equal to c, where c is some constant. Okay? But if f of x is equal to 2, for example, 2 is a constant, then what would that graph look like? Well, then it doesn't matter what value of x you put in here, right? Doesn't matter the input, the output will always be 2, right? And so then it's just this horizontal line at 2. Okay? This is a function, right? Vertical line test, right? Not 1-to-1 though, because they're all to 2, right? So so that's the most basic function that we could talk about. Not that interesting, right? Kick it up a notch. The output is the input, right? If you kind of read it as f of x is the output, x is the input, right? And so here, the identity function is when the output equals the input. Yeah. So start logging that to memory. What does that graph look like? Well, it's this diagonal line where x equals y, right? When x is 1, y is 1. When x is 2, y is 2, right? That's the identity function. Also not terribly interesting, but it's a function, of course. So the toolkit function, so they'll all be functions, but we're just confirming, right? Vertical line test, they're all functions. Is it 1-to-1? Yeah, nice. Right. Each x maps to a unique value of y, in fact, itself. Right? How about the absolute value function? Now, I'm assuming that you've seen these vertical bars before, right around the absolute value. You can think of it as just dropping the negative. We'll see in a little bit that it's a little bit more sophisticated than that. It's a piecewise function, right? But for now, right, it just looks like this. So the output is the positive version of the input. Okay. So here, the output is the positive of the input. Of course, if x is positive, then y is just, it doesn't change, right? And so you could continue and draw this line and then you're back to the identity, right? But now the absolute value function, when x is negative, instead of continuing down, right, on the diagonal, now it flips up and says, okay, if x is -2, then y is +2, right? The positive version of -2. Yeah. So it looks like a V. Good to recognize, right? The absolute value function. Okay. Just that V. That V can move around, right? We're not there yet, but we'll kind of squish it, make it wider, right? All those kinds of things. Okay. But hold your horses. We're not there yet. Okay, so hopefully those are memorable. How about these ones? X squared. I think I've even drawn x squared last week, right? And so it's one of those that a parabola, right? It's parabolic. And so you've got this kind of curvature, right? And you square the input to get the output, right? But I'm not going to write that out because that's what this says, right? F of x equals x squared, right? The output is the input squared. And just to recognize x squared or the graph of x squared, that's all I want for now. And we can do things like flip it upside down, we can move it up, move it down, move it to the side, right? And we can stretch it out, we can make it thinner. No, that's not the term, but I don't have the term. It's not coming to me. More, yeah, thank you. Thank you. Right, so we can manipulate these functions, but we need to recognize the base function first, the toolkit function. All right, how about the cubic? X cubed looks like this. Now all of a sudden it's got a little spring in its step. Yeah. So what's interesting is just from the graph, x squared, we can tell that there are no negative outputs, right? We can take negative inputs, but the output is always positive, right? Same as the absolute value, just slightly different. Right? Now, in contrast, if we have an odd power, and this is true in general, if you have an odd power, then you can get negative outputs. Right? So just in general, these graphs are going to look like this kind of, not really S-curve, but little, what would you call that? I don't know, smooth. Right, so we can put in a negative input and get a negative output, right? And it goes through the origin here. And if we really zoom in, there's kind of almost a flat line there, not quite, but, and then it transitions.
So is that still kind of like, is it a one-to-one or just almost?
It
so close there.
is one, I'm trying to think,
It's like
the proof. I would say it is one-to-one because it's going to be, well, you won't be able to tell from here, but it's going to be ever so slightly changing like that.
Okay.
It's really hard to tell from this graph, obviously. And later in the chapter, we're going to have ways to show if things are one-to-one mathematically. And so then it'll be more obvious, right? But for now, all we have is the visual, right? Does it pass the horizontal line test? And although it's not clear here, it does. Yes. Yes. Oh, the square root function. So of course we mentioned it last day, but there's a little 2 in there, right? But when it's the square root, we don't specify that it's the second root, right? So you can take it or leave it. You can write the 2. There's nothing that's not wrong, right? It's just to save you a little bit of time because it's the most common root. Okay, but if we have some value x and we take the square root, what do we end up with? We end up with this kind of curve. Now, it's not terribly obvious, but it's kind of like taking the x squared graph, and they are related, right? How do I undo a square? I take the square root, right? And so it's like taking part of it and flipping it, and I don't know, maybe it's not that obvious. They've got the same shape though. You have to give me that. But it's not obvious yet. All right. I think there's 3 more. Now it's really gonna pay off if you're able to just look at a graph and match it to a function very quickly. So whatever you need to do, kind of sticky notes around the house or whatever, just memorize them for now, right? And I don't know how you learn, but that's how I do it. I just kind of put whatever I need to learn. Oh yeah. Third root of x looks like that, right? And then you get bored of it and you take it down. So anything other than the second root or the square root, we put a little third root in that crook or the hook, the cranny, I don't know. It's not called the cranny. Right, but the third root of x, now we can kind of see it, right? Sort of the relationship between the third root of x and x to the power of 3. Okay. Some things happened, but the shape is there, right? But it kind of, okay. So they're related, right? Because how would I think of it as undoing a power of 3, I would have to take the third root.
I think the roots are just go more horizontal than vertical. Is that what it is? Like for the cube and the
Yeah. It's a good way of kind of remembering it, right? They're kind of like on the axis. Okay. We're not going to go higher with the roots, but we are going to talk about the reciprocals. So the reciprocal is when the output is 1 over the input, right? So that's the reciprocal, is essentially when you flip a fraction, right? And so the graph of the reciprocal is a little bit interesting because it has this asymptote here. So when x is 0, there's no output. Okay. Why is that? Because we can't divide by 0, right? Division by 0 doesn't exist. And so that's one of the things that we need to keep an eye out for, and that's what we're introducing today. Surprise! It's almost like I planned it. I don't know. So anyway, so we're going to talk about here, there's no output at x equals 0. Okay? But 1 over x, it's got this kind of party going on. And then x can't be 0, so there's nothing here either. But we're going to focus on the x's, the domain. You know what? Because I drew over the graph there, I'll leave it like that. Same thing, if we square the x and take the reciprocal, then of course, all the negative x values are positive, but it's still a reciprocal. So now it essentially flips this and makes it positive. And that's why it looks like that. Notice that there's arrows on all of these graphs, right? It keeps going and going and going and going. In this case, never reaching the y-axis. It gets very, very, very close at infinity, right? But it never touches the axis. And same thing here, keeps going forever, right? But it never touches the axis. All right, let's see here. I made little markings so I could jump around quickly. Now I'll remove it. So now we're going to talk about, so I guess that's the end of our review here. Hey, fit on the page beautifully. So section 1.2, I know I was really aggressive with the first timeline, but that's okay. Wait. So we're going to talk about domain and range. Okay. Now I'm going to emphasize the domain mostly because the domain, which is the all possible inputs. Okay. So here, the domain of a function is all possible inputs. Okay. Whereas the range is all possible outputs. I'm going to focus a lot of our attention on the domain, okay? Because the range just kind of follows from the domain, right? Once you've identified what your inputs can be, then you can easily see what your outputs can or cannot be, right? And so the domain is kind of the most important one, right? And so all the possible inputs, right? So possible X values, right? In terms of X and f of X, all possible outputs would be the possible f of X values. Of course, I'll just snag this for completeness, but that is what we said. I kind of thought he'd have a snazzier way of saying it, but I guess not. Okay. When we're talking about the domain, okay, we can look at it from a graph. We can get it from a graph most of the time, right? But there are a few key things that we need to remember, okay? First one being, we can't divide by 0. So any X value that would force us to divide by 0 is not in the domain. Okay? So here, I'll even do it in pink. That's important. So for the domain, okay, number 1, we cannot divide by 0. Oops, that doesn't look like 0. There. Which means any value of X, which makes us divide by 0, is not in the domain. Which makes us divide by 0 is not in the domain. Good. We already saw the reciprocal function, right? We had f of X is equal to 1 over X. Right, that's the reciprocal function. And we saw how that behaved on the graph, right? It said, whoa, can't be 0 because we can't divide by 0, right? So where X is not equal to 0. It's possible I'm getting ahead of myself here, but we'd end up here anyways. So how about we just go for it? 1 over X plus 5. What's the domain here? X cannot be -5. Nice. See, you got it. -5 because -5 plus 5 would give me 0, right? So that's how we're going to work with the domain, is identifying things x can't be, right? And generally x can be any real number, which is, you know, any number that you can think of between -infinity and +infinity. Okay? But then we take out the pieces that it can't be. It's easier that way. How about the second thing that we need to keep in mind? And I'm only talking about the two kind of most important things here. The second thing is that we cannot take the square root of a negative number. Okay? And so we cannot take the square root, or I should say the even root, but let's just focus on the square root, and I'll put in brackets even. How about? Okay. We cannot take the square root brackets even roots. All right, that's any even root, 4th root, 6th root, etc. Okay. Because of how they behave. Okay, so we cannot take the square root of a negative number. No.
Oh.
So forget about it.
Those are fun.
So imaginary numbers are when you take the square root of -1, right? But we're not. Nah, let's not go there. So you can, but it puts you in a different realm. All right. So we saw if f of x is the root of x, rutabaga. What does the graph look like? Looks like this, right? So from the graph, we could say, well, it looks like x can't be negative here, right? We can take the square root of 0. Now it's not obvious from this graph, right? But as soon as x becomes negative, there's nothing happening here, right? And that's because we cannot take the square root or generally an even root of a negative number. On the flip side, though, we can look at the third root and see, just kind of visually see that, okay, if I give it -2, I get some output. I don't really care what it is. It's somewhere between -1 and -2, whatever. We have calculators, right? But we can see that there's some output, right? So it's only for those even roots. And we're going to focus on the square root. Okay. And so here, where x is greater than or equal to 0, right? Lots of different ways that you can write it, but we'll start. I'm kind of assuming that your inequalities are reasonable, right? If I draw a line underneath, it means it includes 0. If there's no line underneath, it's exclusive, which we'll review in just a few minutes, but it's a warm-up. I used to struggle a lot with the less than, greater than, right? The alligator eats the big number, but then I was always kind of confused. Am I the alligator, or what side is the alligator? So that didn't help me. So it wasn't until I was teaching inequalities one time where a student said, well, I mean, you can just make an L, so less than, with your fingers. And then you just read it like that, right? And so here, if I flip this, then 0 less than or equal to, because it makes the L, x. Or because it doesn't make an L, X is greater than or equal to 0, right? Not an L. You can flip those around, right? As long as I guess the mouth of the alligator follows around, then you're good. Yeah? So I'll say or, you can write that as well. Okay? They mean the same thing. So however, whatever you need to do to remember that, that's, just do it. What would the domain be? I'll do x plus 5 again. It's in a different scenario, similar, but a little bit more work, right? I have to make sure that x plus 5 is greater than or equal to 0. Okay. And so what could I do? I could say, and I'm trying to keep it on this page, but it's tricky. Where x plus 5 is greater than or equal to 0. Which means, so inequalities, I used to cringe when there were inequalities, but it's really if we're just multiplying or dividing by a negative number, then it switches the side. Otherwise, we can treat it as just an equal sign, right? So I'm allowed to do x minus 5 on, or x plus 5 minus 5 on both sides to move this 5 over. And to keep it on the same page, I'll just do this. So x has to be greater than or equal to negative 5. Now, whenever I do these, because I'm always a little rusty, right? I like to just put in the value and do a couple of test values just to make sure that it makes sense. And so if x is negative 5, let's start there. Then negative 5 plus 5 is 0. I'm allowed to take the square root of 0. It's 0. Okay. But I'm trying to avoid negative numbers. So greater than or equal to negative 5. Okay. So now I do negative 4, right? Because negatives are weird, right? You add, as you increase, you're moving closer to 0. Right? So negative 4 in here, negative 4 plus 5, phew. Okay, so it checks out, we're all good, right? But it's good to kind of pick a couple of values, right? An easy one would be let x be 0, right? That's greater than negative 5. Put that in. Okay, phew, back off, that's good. Okay. All right. So we can usually visualize the domain, but I think the safer thing to do is just remember those two key things for now, right? You can't divide by 0 and you can't take the square root of a negative number, okay? And then it's better to just kind of do the math. It's not hard, right? As long as you remember what you're looking for. Okay, so no, Emily, bad. I was gonna make us guess what the square root of x plus 5, the graph of it might look like, but I said no, be good. Be good. All right. Oh, that's not where I want to be. I want to be in the examples. Okay. So we're going to have kind of technical domain and ranges, and we might have kind of reasonable domain and range. Okay. So for example, we can have, I'm going to call it a technical domain and range. Or reasonable domain and range. as in this example. Now I'm gonna kind of breeze through this because I'm typically not interested in reasonable domain. Obviously, it's a good kind of jumping off point, what's reasonable, right? But usually we're dealing with functions, and so then we just want to know what can X be, what's the output, that kind of thing. But if we have some sort of function where it takes your age and it returns the average height, then, I mean, technically the age, you have to be older than 0, right? 0 or older, right? And technically the age can be infinity, right? It's not reasonable, hence reasonable domain and range, right? But if the output is the average height, again, we can't be negative height, but we'll allow anything above 0, right? Technically anything from 0 to infinity. However, there's a reasonable domain, right? Where we would say, whoa, someone's 17 feet tall, huh? That doesn't make sense. So then that's not reasonable, right? It's not in the reasonable domain. But I only want to introduce this just to kind of get our feet wet in the domain and range. And then usually we'll just rely on the kind of technical domain and range. Okay, and so technically, age is the input here, right? F of age, average height being the output. So technically, age can be any value between 0 and infinity. A reasonable age, right? Let's say, but the reasonable age, I don't know. We don't know what the function looks like. So let's assume that it can take anything from 0 to 120. After that, who knows how tall you are? I don't know. But should we push it to 1? How old's the oldest person?
If it's average height, shouldn't it be average life expectancy?
Yeah, but well, I mean, yes, it's just an example though. But so if you're 30 years old, what's the average height for a 30-year-old, right? If you're 120 years old, what's the average height for a 120-year-old, right? How old is the oldest person? Hey, Google.
It says the oldest person to lived to 122.
Lock that in. So I was pretty close with the 120. Feels extreme, but I guess I could go as far as 125. The point is there's a cap, right? We could put 400 in, but it's not reasonable, right? And same thing with the average height. Okay. So even if the average was the same as the tallest person possible, it's all trivia this morning, I guess. Right. We wouldn't accept an answer like 8 feet tall or something like that. It's funny because I'm completely metric, but then when it comes to height and weight, I've kind of gone imperial. Feels icky, right? But I don't know why. I don't know how it happened.
Well, that's just Canada in general.
Yeah.
Right? Yeah. So, I mean, the range, or I guess this is the domain. I didn't specify. The range, again, technically 0 to infinity. Oh, that's not a very nice infinity. I'll write it out. Usually because my infinity doesn't look very good. It's like a little flat pancake. I'll draw it here so that you can identify it later. But hopefully you know the infinity symbol. It's an 8 on its side. Okay. But the reasonable range, which is the average height, if someone is 0 years old. There's even a minimum that's not 0, but usually what we do is we kind of allow it, say, okay, well, yeah. But once you're born, you are some length, right? So on average, some height, but I'll go with 0 just for simplicity's sake. 0 to 2.5 meters there. I'll buck the trend. I feel like that's extremely tall, right? I know I'm 171 centimeters, or I used to be. Maybe I've shrunk. But 1.7, 2.5, that's nuts. I guess it can happen, but for the average, it's a little bit, it's extreme, right? 2.5 meters compared to infinity meters, though, now we've got this kind of reasonable range that we're thinking about. Okay. So notice that we are talking about these intervals, right? 0 to 122, 0 to 2.5, and we've already seen inequalities. So there are a couple of ways that we can communicate these inequalities or these intervals. Okay. So we have a few ways, oops. To communicate intervals. First one being interval notation. And you know what? I'm sorry. I'm going to give myself one line. I want to do, just as an example for each of them, X is between 0 and 122, right? That's in words. That's inefficient. Let's say exclusive of 0 because you have to exist, and inclusive of 122, which means that X can be up to and including 122. Okay. In interval notation, okay, how can we denote this? Well, we go from the smaller value to the larger value, and we separate those by commas. And how we denote the exclusive or inclusive is by a round bracket and a square bracket. A round bracket meaning not exactly 0, right? It can never be 0, it gets close to 0. And then a square bracket says, yeah, you can go right up to 122. So it would look something like this. Okay. Where, right, a round bracket is exclusive of 0. And a square bracket is saying, yep, 122, including 122. So including 122. What's the, I guess the second one, we could draw a number line. Same thing, we need some way to communicate inclusive, exclusive, right? And so we use an open dot or a closed dot. So maybe a number line. Usually we just use it to visualize things. It's not the best way of communicating. Oh, draw arrows because it keeps going, going. But the possible values here are 0, exclusive of 0, so not including 0, and all the way up to 122. And then you just draw a line in between here. All right, all those values up to and including 122, but starting at 0, but not quite 0. Yeah. Same, but different. Yeah. What's the third way? A little bit more sophisticated, right? We could talk about in terms of inequalities. Inequalities, which in this case, right, we would say X is greater than 0, right? Not including 0, so no line underneath. Or if you want to read it as 0 is less than X. Yeah. But then I'm going to put the top half on the X as well in this same breath, I guess. Less than, so X is less than or equal to 122. Yeah. So we could use those inequalities. Okay. All of these say the same thing, right? And if you have a choice, you can use whichever one of these you gravitate towards. Right? Usually I'll ask, use inequalities to express the domain. Right? Or finally, building up to set builder notation. So set builder notation looks like this. Oh, that's a curly left bracket. My curly brackets are never that good. I'll try again. Nailed it. So we use curly brackets to denote sets, and sets are just groups of things, right? Elements. But set builder notation has this general layout where it specifies what you're talking about, okay? And then we draw this vertical line as opposed to the other vertical lines, like the absolute value that we've seen before. Now in set builder notation, you read this as such that and then we throw the inequality or any sort of condition such that X, and in this case, X is between 0 and 122. Oops, and then close that curly bracket. So it's just a fancier way of writing inequalities, but it's just more technical, more complete. Okay, so how we read this is X such that X is greater than 0 and less than or equal to 122. Don't worry, I'll write it out. Is read as the set of X, okay, because it's in set builder notation. So the set of X such that X is greater than 0, and less than or equal to 122. So that's how you're going to read that. Okay. Most of the time, the domain and potentially the range is just the set of real numbers, okay? Notice how I'm saying the set again, okay? And so it's this established set, okay? So most of the time, the domain, I'll say and range, but like I said, I want to focus on the domain. The domain is the set of real numbers, is the set of real numbers, which we denote by this fancy double-backed R. Okay. So the set of real numbers, here I'll highlight it. It's important to recognize it. You just draw a capital R and put a double back on it. And then you have the set of real numbers. So the set of real numbers is the set of X such that X is between -infinity and +infinity. So it's any value between -infinity and +infinity. Right. I can't be including infinity because there's always more, right? So you'll never reach infinity. It's kind of mind-boggling, but yeah.
Could we use the, I don't know the name of it, like the little lowercase c, like X is a member of the real?
Oh, yeah. Or you can write exactly, or X is in the set of real numbers. Set notation here. Okay, so this you read as X is in the set of real numbers. Nice. Which is just saying X is anything between -infinity and infinity. And often what we say is, so before when we were talking about our kind of baby domains, right? X can't be -5, but what were we implying? It can be anything but -5, right? And so then X is in the set of real numbers, but not when X is -5, right? So we put that exclusion on there. And so generally X is in the set of real numbers, and then we tack on whatever it can't be. Right. Nice. All right. So let's do a little bit of practice. I think we're gonna write each of these in interval notation. Sorry, I did get carried away here, but so now back to some breezy stuff. Yeah. So the first one, right, an interval notation is just when you use the brackets, right? Round brackets. So round versus square brackets. So the first one, it's starting at -3, so we always list our numbers from smallest to largest, because the other way it doesn't exist. There is no interval between the two. Just me being picky. So x can be, is any value greater than -3, not including -3. And so I denote that by a round bracket. All right. So -3 up to 4, including 4. All right. Square bracket. So you want to be really careful with your brackets, right? You don't want to just, they mean two different things now. Okay. Oh, I'm noticing I forgot to introduce something, the or, but that's all right, can handle it. Let's write these two inequalities out as intervals, and then we'll look at the union of them. So here, it's the set of x's such that x is greater than or equal to 2, but less than 5, or x is greater than 8. Okay. So we'll look at those two individually, and then when we have the or, okay, spoiler alert, or we write with a capital U for the union. To link those up. So here, so I'm going to tackle both individually and then link them up with a U. And same thing, I think, because you'll have to enter these in MOM, right? Just use a capital U to link them all up, and it'll work that way. All right, starting off with 2, which is our smallest value, round bracket, square bracket, square. I know. I never actually asked questions because I found it really stressful as a student, and I'd be just pretending to write the whole time. Oh no, I'm still no. So
I do have a question though.
yes.
With the union, would you also sometimes just use a small v or
In logic, yeah. So you can use a v, yeah, for the intersection. Yeah. For and you use an upside down U or an upside down V. Usually we use the V's for logic, but it depends on what field you're in, and it can be used for sets as well. Yeah. Up to 5, not including 5. Gets me a round bracket. I know it's killing me that I don't have it on the line, but when I print the PDF, it ditches the lines anyways, so it's not forever. And then x greater than 8, not including 8, right? So the lowest value would be 8, but not including 8. And then I can take it to infinity. Round bracket, because I'll never reach infinity. That's the whole point. And then I can link these up with a capital U, and we read that as the interval from 2 to 5, right, including 2, excluding 5, or 8 to infinity, right, x greater than 8. Nice. Set builder notation, which, right, is this little guy here. Takes some practice usually. So let's see here, we've got, so write these in set builder notation. Try to line them up with some lines here. Okay. And there are often a few different ways that you can write these, right? If you don't want to talk about the inequality from 3 to 6, right? Greater than or equal to 3, less than 6. You can break those up, right? And say x has to be what? Greater than or equal to 3 or less than 6. Well, technically and, but I haven't introduced it yet. But I'm going to stick to the script. Set builder notation starts the same way. So we have the set of x such that, notice how it always starts like that. So it looks more complicated and looks fancier. But then we just talk about the inequality after that anyways. So such that x is less than, or sorry, greater than or equal to 3, but less than 6. And that describes the set. Same starting point, right? If we're wanting set builder notation, curly, whoa, that was a nice curly bracket. Enjoy that one. The set of x such that x is between -infinity and 2, not including any of those endpoints, or 3 inclusive up to infinity, right? So you can write the word or you can just keep the union just to make it look a little bit different. I'm going to write the word or. Okay. So it's the set where x is greater than -infinity up to 2 or 3 less than or equal to x less than infinity. Hey, those, even my right curly bracket looks good. Wow.
So can you put the capital U instead of or inside your one set?
Yeah.
Okay.
Yeah. So as soon as you see this U, you can interchange it with or U, doesn't matter. So yeah, I would write the U in here probably. But then it doesn't really change. All I did was change the interval notation to an inequality. And I guess that counts, but it's not that crazy. All right. We can look at a graph. I will say that there are a couple of things to keep in mind if you're just looking at a graph to figure out the domain and range. So far, we've just been talking about the domain, right? The possible values of x. Okay. And let's have a look here. Oh. Okay. Oh. One page. Just off. All right. So if we have a graph like this, and if you want kind of more, what's it called? There's a website, Spurious Correlations, I think it's called. See spuriouscorrelations.org or something probably. .com or org or something like that. Anyways, they have all these. So someone has spent a lot of time figuring out all the things that are highly correlated. Correlation meaning they have a very strong relationship together, right? And I think without any kind of prior knowledge, we can look at this graph and say, whoa, that's a really strong relationship, right? You can see as the years go on, right? then what are we actually looking at? If we think about X as the input and Y as the output, well, then we're saying that as the fresh lemons imported to USA from Mexico in metric tons increases, then we see a strong decrease in the total US highway fatality rates. We understand that those two things have nothing to do with each other, but there's a very high correlation. Okay? The correlation squared is R squared. Now we're in stats, so you can tell that I'm like, this is my jam. So here, the closer to 1 you get, the stronger the relationship is, right? The closer these dots are to the line, as we can visualize here. But it's just kind of these things happen, right? And if you go to spuriouscorrelations.com, a lot of them are fine. A lot of them are a little bit morbid, mostly to confirm what it is. Oh, well, I guess it's tylervision.com, but whatever. You really claimed it. So the US spending on science, space, and technology correlates with the suicides by hanging, strangulation, and suffocation. They're all morbid, or most of them are morbid just because that's what we have data on, data available to us, right? That's of interest. How are people dying? We want to know that. But also a number of people who drowned by falling into a pool correlates with films Nicolas Cage appeared in, per capita cheese consumption, tangled in their bed sheets. Yikes. And well, there's lots more, but divorce rate in Maine, per capita consumption of margarine. Don't eat margarine, guys. Or maybe do eat margarine. I can't. Don't eat margarine. Yeah. Divorce is bad. Age of anyways, so kind of fun. I know you want to know what this one is. Age of Miss America, murders by steam, hot vapors, and hot objects. Anyways, the list goes on. He spent a lot of time on that. So you can go check that out. None of those relationships are linear like we see here, right? So you would need another shape instead of just the straight line, ta-da, to describe them. But from here, we can talk about the domain and range. What are the possible inputs? Now, in this case, right, the line does not keep going. Okay. So in this relationship, it looks like the minimum value of X that we can have. I'm just going to go to 200 because I'm not that picky. Should I be? I don't know. Maybe. X, so the domain, I'm going to go like this. 200. I'm not going to close it because I don't have a point at X equals 200, but roughly. Okay. And up to a maximum of 550. Again, I'm not going to close it. If I had the values, I would be able to say what the exact values of X are, but I don't. Up to roughly 550, right? For this relationship. Okay. What does the range look like? The range here looks like it's from about, I usually just take whatever values are on the axis. I'm not, without the data, I don't care to be too specific here. 14.8 to 16 are the possible output values. You can see that it's a little bit less, but on either end, but Y, because we haven't been writing about range, let's mix things up. Y is greater than 14.8, but less than 16, right? Or if you prefer, f of X, right? But I tend to just swap them out mentally, use them interchangeably, whatever helps, especially when I'm talking about a graph like this. Oh, I don't know what happened. That's the y-axis and this is the x-axis, right? So then it helps me to think of it as y instead of f of x. All right. So, oh yeah. So in the textbook, of course, he goes through and he holds your hand and looks at all the different kind of relationships between an inequality, set builder notation, and interval notation. But because I want to introduce piecewise functions, I'm gonna skip ahead. Okay, so he does talk about the domain and range for all the toolkit functions. So have a look at that, confirm with the graphs that we saw at the beginning today, right? And just make sure that those map to each other. But I'll leave it for a little bit because we already talked about things like, okay, once we see the quadratic, the range has to be positive, right? You can take 0 squared and get 0, so it includes 0, right? And he's got a little description here as well. So so have a look at those. That's page 27, 28 in the textbook. The reciprocal and the reciprocal square, that's where we run into trouble, right? Because we already established that 0 is not in the domain. How does that affect the range? Right? So he says we cannot divide by 0, so we must exclude 0 from the domain. We already got there. 1 divided by any value can never be 0, so the range will not include 0. All right? That kind of thing. Let's talk about, just finish on a piecewise function, because sometimes our functions behave differently for different values of x, right? Different values in the domain or inputs. So a piecewise function is a function in which the formula used depends upon the domain the input lies in. Okay. So how we denote this is by using this kind of big curly bracket here. Okay, so now f of x equals more than one thing depending on the input. Okay. And just in general, read it as, okay, use formula 1 if the domain is this, right? And usually we work our way kind of from negative infinity all the way to positive infinity. For these domains, you want to list them kind of in the order they appear. Okay. Use formula 2 if the domain is this, right? Use formula 3 if the domain is this. You can keep going. Usually we start with just 2 functions here or 2 different formulas, but you can have as many as you need, right? So, got an example. To think about. So we're going to write a piecewise function to describe the cell phone plan. It says, okay, there's a base $30 fee. So regardless, you're going to pay $30. We're all kind of well versed in this, right? So you pay $30, or I mean, that'd be great, but I pay a little bit more, which includes 300 free text messages. Those were the days, right? And each additional text message costs 10 cents. Okay. So you all the way up to 300, right? Your plan is $30. Okay. So how are we going to denote that first part of this piecewise function, because what happens after 300 texts, then you pay 10 cents per message, right? So what's our input? Let's start there. Our X should probably be the number of text messages, right? How much we pay seems to depend on the number of text messages. So X is the number of texts. And then the output, F of X, is going to be the total cost. Right? Let's start there and identify the input, the output. Right? All right. So then F of X, which is the total cost, which is what we're interested in, is going to have two components, right? And so I'll start with a curly bracket, whoops, that spans two lines, right? Because there are two pieces to the function. I'll start with the easy part, right? Because as long as the number of texts is less than or equal to 30, I'm gonna go equal to. Let's see what I did. Yeah. Okay, I agree with myself. Hopefully you do too. Up to and including 300. Right? That's something I guess you would want to confirm, but with your provider. But the output is going to be $30. And then we just write if the number of texts is less than or equal to 300. There's that implied condition that X has to be greater than 0, right? You can't send negative messages. So I guess we could tack that on for completeness sake. I guess 0 is included. Just logically, you could send 0 messages. That's allowed. It's hard, but it's allowed. All right. Okay. So that part we're okay with, I think. Now it's the pickle of now that X is, so let's talk about the condition on X first, right? If X is greater than 300 and there's no, if you hit 500, then it drops down to 5 cents a text or something like that. You could keep going with it, right? And have multiple pieces in your function. But for us, we're just going to say if X is greater than 300, if you want, you can put, but less than infinity. It's implied. So that part's optional, right? You don't have to go there. I like to have symmetry around my X's. Right. So I throw it on there. So any X between 300 and infinity, not including 300, and obviously not including infinity, is going to behave like what? Well, I have to pay the $30, the initial $30, that's still there. And 10 cents a message after that. But the messages are being denoted by X. And so what's that going to look like? 0.1 X. And I know I'm out of time, but this looks like a straight line, right? With a slope of 0.1. Right? And so got a constant function, and then it increases with each message after 300. Nice. Okay, so we'll pick up there on Wednesday because I'm out of time. If you have any questions, let me know.
Would it be like technically, would it be 0.1 times X minus 300? You don't want to charge that.
Oh my gosh, thank you. You guys were just gonna let me go there?
Yeah.
You know what, I should do it in red. I was also excited to leave. First 300 are free. Sorry about that, guys. Thank you. Now I can stop the recording. Forgot a critical